Hi, my name is Anthony Skokosis, and I present joint work from the National Technical University of Athens and the Chalmers Institute of Science and Technology in Sweden. This presentation holds two different promises. One promise is to present a different way to perform the LCA, not with a view to replace the good use of LCA today, but to offer an alternative approach that could be very useful in decisions at early stages of design. A second promise is to explore advanced analytics and machine learning to bypass tedious and time-consuming stages to calculate life cycle inventories. Now, the challenge for the Ex-Ante LCA is definitely not new, but is definitely also well reported as one of the most important for LCA. The presentation picks up on this challenge and gets assistance from advanced analytics, explaining results, which we consider are quite promising, and are illustrated with different examples. So this is the outline of the presentation. I will first elaborate on the challenge, and then I will try to explain the problem and the methodology. And as I said, I will share some results for two domains. One, the one that we promised in the abstract, which is the biorefineries. And I will also explain, how we have expanded this recently to consumer products, an indication that the methodology that we present is generic. Now, LCA is running for almost 30 years, and has been produced, not within chemical engineering, but chemical engineering definitely has quickly embraced LCA and now is part of our routine calculations, for designs, and case studies. It is essentially an ISO that has four rigid and clearly defined stages that include, the goals, the description of the boundaries, the calculation of the inventories, and the development of analytics. LCA has definitely also expanded our perspective, from the previous esoteric, analysis of the process into one that considers both upstream and downstream process, what we would consider a holistic approach. Also, LCA is involving a lot of data, background data with respect to the products, the process, the reactions, foreground data, which relate our decisions, to ways to implement our idea into a process, and output data, which is the performance kind of related data, all the different type of metrics, midpoint, endpoint categories, and so on. So what we have today, the ex-post type of LCA, is data flows that are shown here from the left to the right, include the background data that are converted to foreground data and then eventually give rise to life cycle inventories and life cycle analytics. Again, we want to get quickly through the foreground kind of evaluations and much more to make use of our degrees of freedom to get to better LCA performance, not just wonder how we're gonna improve, things that we have produced. So what we need is support as to the overall development of the background data, so the means, in other words, to go through the foreground calculations quickly and also make a good use of the degrees of freedom so that we get to better results. So what we need is actually advice at early stages of development, so advice in advance. So advance is exactly what Ex-Ante stands for, but what in advance for? So going back to the data structures, for the ex-post calculations, what we need to know is means, to possibly change our flowchart with better processes, with better means to integrate, with different alternative supplies, if you wish, even to change our, initial kind of idea into an alternative idea. So the ex-ante promise has to be able to exclude technologies, ahead of design, build functions that identify good supplies from bad supplies, means to target appropriate products and product portfolios early on. So from a viewpoint of data flows that we started from, again, input comes from the background data, the output is the LCI, and the foreground is the in-between stages, if you use the system that translates the input from the left to output on the right. And this system takes time to deliver, and this system could be parameterized to deliver with respect to the degrees of freedom which are available for us to manipulate. So the basic idea is to use foreground, data in order to develop a data model that could replace or convert the conventional way or conventional, connection between input and output from the flowcharts that we conventionally use through a data model that could be in the form of a decision tree or an artificial neural network. And apparently we will use machine learning in order to develop these models. So from a systems perspective, what we are given is a data sets of background and foreground data, a set of KPIs, and we want to develop an inventory-free model using machine learning technology. I will start with the presentation of the input-out-based data structure that includes choices for background data that relate to reaction paths and chemicals, products, product portfolios, and different type of processes. We have sets of data that for each product could originate or will originate alternative supplies. So in this case, from glucose, we have supplies from wood chips or wheat straw, and many more. We have sets of data for each supply to address options to produce different products. So in this case, from biomass, we produce methanol, ammonia, ethanol, and many more. And we have another set of data to connect supplies and products to different technologies through, in this example, biochemical or thermochemical routes. And the choices for foreground variables include all different types of generations, first, second, third, fourth generation, biorefineries, from more mature technologies like the biodiesel, bioethanol, biogas production, down to more emerging ones like the algal biorefineries and waste biorefineries. In terms of numbers, the foreground sets, that we have used in this study include 92 non-integrated flowsheets and 80 integrated flowsheets, overall 52 processes, 32 products, and 5 different types of biomass. Multiplying all these, we have 3 different options for calculating the allocation, either based on physical and economic parameters or based on system expansion and substitution. Overall, the output of the system accounts for 138 different KPIs, which include the 23 LCA metrics, namely the midpoint impact categories, the endpoint damage categories, 2 different totals to score metrics, and all this multiplied by the 3 allocation methods that I explained before, and 2 sets of independent variables for fully reduced kind of systems. The machine learning technology comes with 2 different options, decision trees and data models. Classification technology is used to develop the trees where the variables, the dependent variables, are discretized in different classes. The 80-20 standard split for the data sampling is applied in the training process. The artificial neural networks, include both in-house developments and over-the-shelf kind of developments. And the results out of the validation stage are shown here. We have picked up models with error less than 20% that are aligned with the kind of error we expect at the early stages of development. We have verified the joint importance of both process-related and product-related functions, in the models. Examples of trees are shown here with respect to the climate change, with respect to CED, the cumulative energy demand, with respect to the human health. And again, these kind of trees are developed for all these different indicators, that I explained before. And as far as the artificial neural networks are concerned, they generally worked well for the majority of the metrics. Still, some of the indicators, for some of the indicators, the performance has not been the best, and there is room to improve this part in the future. I will continue with some examples, to get to the essence and the actual usefulness of what we do. 3 different examples are shown here. One that relates to the product portfolio, the other one for selection of technologies, either with only decision trees or with a combined use of decision trees and artificial neural networks. The first example is about selecting the best product or the greener product out of choices that may be available. We have 2 different metrics, the climate change and the cumulative energy demand. We have wood chips as the raw material. So again, the idea is which one of these products is better, and and all that, without the need to do any simulations. So to do that for each product, for each feedstock, for each technology, we need to rely on the decision tree. We pick up the numbers there, and then the results are summarized in the tables. The first column gives the estimates from the decision tree. The second column gives the detailed calculations of the LCA, and as we will see, both for CED and the climate change evaluation, they coincide. So not only that we have picked up the right products, but also we are able early on to identify green or sustainable or promising type of flow sheets, to analyze. And the second example, the purpose is to identify the right technology to convert lignocellulosic biomass into glucose. Options include steam explosion, direct hydrolysis, and organosolid technologies. We pick up climate change, as the metric, to choose. Again, decision trees. Again, for each feedstock product technology, we have to apply the tree. And the results from this analysis are shown here. The first column, again, is the estimates from the decision tree. The second column is the estimate, results from simulations. And as you will see, the 2 match 100%. In the third example, again, we address technologies for a non-conventional product, the dihydroxyacetone, that comes, from plant oil or waste oil. We use climate change again as an environmental metric, and essentially we have to evaluate ahead of design calculations for different paths, these paths that we show here. The result in the first column again is the estimates that are not matching now the detailed calculations. They consistently underestimate the impact. 2 cases, 2 paths were found with medium impact instead of high. Still, the green solutions were, the green solution was identified as the last one. Now, also, if you or one uses artificial neural networks on top of that, we'll be able to identify the single better solution, the last solution, as the greener one, and definitely, pick up the right one. So a combined use of artificial neural networks with decision trees is what will give you the better result in this case. Now, although the work is at very early stages, the results are not so bad, I would say, and more data will make the models apparently more reliable, especially with the joint use of decision trees and artificial networks, to double check, for consistency. We have actually whet our appetite with this kind of work. We have already extended the application into consumer products, believe it or not. This is joint work with Whirlpool, and an Italian group. So what we target now is electrical appliances. Yes, it's a different problem. And we want to identify what are the better materials, to use. So instead of flow sheets, here we have bill of materials, full material disclosures, and LCA calculations as before. At the end of the day, we have also foreground, background data and LCI metrics. So the idea is more or less applied in a very, very similar way. So again, background data will be the FMD, and the bill of materials will be the foreground data. And again, the output will be the LCA performance. The ex-ante approach appears to be getting a lot of useful help from machine learning, and we continue along these lines. Unfortunately, time is running out and we cannot show more results for this other application, but probably in the next presentation we'll be able to do that. In the meantime, I would like to acknowledge, partners in different projects that have contributed to that, and definitely our sponsors from the European Union in 3 different products for that. And with all that, I would like to thank you and be apparently ready to answer questions.